hello everyone. Very big audience. So I was already introduced. So yeah, I'm from Fraunhofer IPA and the ROS-Industrial Consortium Europe. And you can basically see here our laboratory in Stuttgart with a lot of robots. Yeah, and okay. Does not switch if I press. Now it's switched, okay. Yeah, I also wanted to give you a short introduction to Fraunhofer in general. So Fraunhofer, I think, is a bit similar to A-Star. So it's a relatively large applied research organization. Which is based in Germany. We have something like 30,000 employees with roughly 76 institutes. There's always one more at some point, so I don't know, maybe now it's more. And a budget of 2.9 billion euros per year. And yeah, so that's Fraunhofer. As I said, there's 76 institutes. We are one of them. We're one of the three biggest, and that's Fraunhofer IPA, which is basically based in Stuttgart and works on automation and production engineering. We have a budget of roughly 82 million euros per year, of which basically 23 come from industry. We have roughly 1,000 projects per year. And roughly 1,200 employees, though that's to be seen. There's also student employees in the 1,200. We have roughly 400 research engineers at Fraunhofer IPA. Yeah. And now, okay, we focus down on the people that are actually doing robotics at Fraunhofer IPA. So that's basically the robotics department. Actually, this year we had our 50 years anniversary. Well, we basically brought robotics to Germany. At least that's our version of history, you know. So right now we have roughly 70 FTEs in our robotics department. Okay, we also have a few robots that work for us. We are split in 8 teams, and the robotics department has that operating budget. We are basically focusing on a couple of different technologies. So that's basically the groups that we have. You can see that on the bottom here. So we're working in picking and packing, welding, industrial service robotics, assistance robots, robot programming, software engineering. That's actually my group. So yeah, that's also later in the slides you will see I'm a bit biased, yeah. And then we have assembly, automation, and safety. And yeah, that's basically my team. So that's the ROS-Industrial team that we have in basically our institute. So you can imagine that, okay, we are on the one side basically catering to the ROS-Industrial Consortium Europe, so basically to our members and producing technologies with them and for them. But as you've seen, we also have a quite big robotics department, and we're also basically providing the base technology for all the technologies that we're developing in robotics in our institute. So that's our guys here, and yeah, women as well. And I also wanted to show you a bit, okay, how are we actually working at Fraunhofer IPA in terms of, yeah, what is actually fueled by ROS? So on the one side, Fraunhofer IPA has a lot of basically public funded research projects that basically go a little bit more into basic research, creating new technologies. So this is a couple of them. For a few of you, probably ROS-I is a name. So that was basically an action that actually helped us in Europe setting up the ROS-Industrial Consortium and making it bigger. Was funded by the EU. And then now we have a very, very large project that is called AI Matters that you will probably be hearing of in the next 5 years, which is basically focusing on providing test environments for AI technologies in the realm of manufacturing engineering. I'll be showing a few things about that later. And that is things that we've done with ROS, actually. So, for example, let's say, where did we start working with ROS as Fraunhofer IPA is basically with the CareWatt 3. That was in 2009. So we had a couple of our, I I think 1 or 2 people of our institute went over to Willow Garage to work with ROS, and then basically we have been working on different kind of things. You can see actually in the beginning we were mainly focusing on really hardware, so we built the robot work, the care robot, and then you can basically see here we have a lot of things that are actually only software. And we've been quite successful in bringing them into industry via startups on the one side, so you can actually see these are the technologies that we brought to industry as a spin-off of Fraunhofer IPA. And then we have a couple of other softwares that we basically licensed out to a couple of companies. So I think the latest one is also the one that will probably have the biggest impact. So that's basically for robotic welding. So we licensed that to 2 companies, Lorch and Trumpf, which are relatively big in the welding market as far as I know. Yeah, that's basically some of the startups. But that in terms of, okay, how do we actually work? How do we bring technology to industry? And on the other hand, you can then see here, so that's a bit of our agenda, what we want to do with ROS. On the one side, you can see, if you look into industry and you look at the software that generally is used to control industrial robots, basically reusability is not really a big factor. So we know a lot of companies that just build their machines every time from scratch or by copy-pasting stuff, yeah? That is not what we want, actually. We want to really have reusability. And then when we have reusability, we have a lot of modules that we can put together. And there comes in, okay, we have composition. So if you ever have built something like a care robot, you know, okay, ROS gets pretty complex if you have a lot of nodes. So in the end, you actually should have tools to make that simpler. And that's one other factor that we're focusing on. And then the next thing that is a little bit new to us as well is that we said, okay, once you have a system, how do you actually make sure that it's ready for industry? So you need to basically have a third level that is basically focusing on validation. So that's the ideas that we have in that term. And this is what we do in our group, or what we actually try to produce. Is on the one side, integration tools, as I said. So basically you need to take what is in the ROS ecosystem, put it together to something that really works for you. And that is basically then the step of system integration. And then in the end, we also want to provide you help with the system testing. So that's basically what we do in our group in terms of work for industry. And this is one of our latest projects. It's basically, we have been working for a couple of years. For those that have heard already my previous talks, we've been working on this model-driven system composition tool that is based on Eclipse. And we've now integrated as well with behavior tree CPP. So in the end, you can, based on that, model your whole system and generate basically a deployment of that, which means basically launch files that launch your system in the way that you want to have it launched, plus put together all the source code that you require. And then you can use right now platforms such as GitLab or GitHub to basically build Docker images of what you want to actually deploy in terms of application. And then you can deploy that. Right now, we're focusing on a couple of different execution platforms. So the nice thing is that I think industry has become aware of that only having a PLC as controller is not the way to go anymore. So we have now a couple of really innovative new PLC types that allow you to as well run, for example, a Docker image or similar things on your PLC directly and directly communicate with your for example, a system such as ROS. So we have basically this kind of a system integrated with Phoenix Contact. We're working on it with Control X, so it's not 100% there yet. And Omron, we basically use the OPC interface still. But maybe at some point they also provide something a bit more advanced. And with that, we can then actually control all kinds of industrial hardware because we basically can leverage the best of both worlds. So for example, we can control the industrial robots with the ROS driver, but then we can connect to, for example, something like Festo, pneumatic islands, via the PLC controller that we have on the PLC. This is an image of what we do in terms of modeling of applications. So here you see a relatively simple pick and place application that is being modeled. And what I wanted to just point out is, okay, the great part is if you have a model of your system is that you can actually change it depending on what kind of hardware you have. So you can actually see here, it looks pretty similar. But then you have two parts that are different, and that is this part, which you can see here on this side, that is actually the gripper. So we changed the gripper, and we have another driver for the gripper, and then we also changed the robot. So you basically see that orange part down there. That's basically what has changed to change the robot. The rest stays the same. And that's basically the simplicity that you have. Similarly, for behavior trees, in the end, nothing has to change if you have such a basically framework below. You can basically use the same behavior tree, except for a couple of small parameters that you need to change on the different system. We have a great demonstrator for that at our institute. So if you ever wish to come, just contact me and check it out. Otherwise, we've also now integrated this with GitLab here. So in the end, the whole flow, basically, you can control that from the cloud. And in the end, I don't know, where's the play button? Somewhere's the play button, Ansible deploy. You can then basically deploy it to your robot controller, and you're ready to go. So that's basically all built on open source software. I know there's a couple of different companies that are doing similar things, but yeah, we're trying to do it open source as much as possible. So you basically find the behavior tree CPP, you find that online. There's basically our code that is called a ROS model. You'll also find that on GitHub. The deployment is not yet released. Yeah. Okay, now we get to the next part. So here is basically a bit of the test fields that we use for developing this technology. So the first one we finished in 2022. With basically 3 robots. You can see that on the down here or down below here. Yeah, with me running in the picture, great. Yeah, in the end, that was one of the first test lines that we have here to basically use that system, model everything. And yeah, at that point, we weren't yet using behavior tree CPP, but we had basically an implementation in ladder on the PLC. That was not the best idea. So in the end, the company that we were working with at that point, they were super proud or they're super happy of PLC programmers because apparently they have a lot. But in the end, they noticed, okay, we cannot maintain such a thing. So now we basically went over to the next iteration. So that's what we hopefully will have done in Q1 2024. That's mainly a hardware availability issue. So there we're going to build a similar line that's basically going to be a different process than we have here. So we're going to focus on DIN rail assembly because that uses a bit of force-controlled assembly things. And there we're basically going to have the whole behavior specification done in behavior tree CPP based on ROS, and PLCs will only be used as, let's say, easy hardware access anymore. So the whole control flow will be in ROS in that case. Okay, now I talked a lot about our system integration tools, and I also wanted to go a little bit into what we do in terms of creating environments for testing ROS. So one of the big issues I think is right now, if you want to build a ROS application, is that you need to know what hardware can we actually use. I think we have seen a lot of talks today about, okay, yeah, we have great software that we can use, but in the end in robotics, software is just one part. So one step that we want to do here is that we create some kind of a reference cell where we actually have a couple of components that are well tested, well in use, so that basically people have the ability to relatively easily test their new solutions, their new software on a system. So first step to that is for us designing a robot cell that is, let's say, relatively cheap, but still industry ready. So our current status on that is basically you can see here on the left the first cell design. So that is done, And we've ordered 2 of those, and they have arrived now, so we're currently in process of setting up. And yeah, we are basically now trying to get a couple of ROS2 robots together that actually we have tested and can say they really work, and how to actually set up the drivers and so on. So that is basically that list, and we are basically, we've seen that before, we're focusing on these 3 PLC types, and a couple of different peripheral equipments in the first stage. So that's work ongoing here. So we're trying to as well standardize a bit the hardware interface to make this a bit more modular. So there we're using a bit, let's say, the German engineering capabilities. So you can see there this 50 times 50 table. So that's basically a pretty common thing that you use in welding for positioning the pieces that you want to weld. But what we've noticed is that this is really a thing that you can as well use in cells that you basically want to reuse for different purposes. So it's very accurate positioning and very well fixed. We have basically 2 of these in the cell, one on top or one on bottom, so you can basically mount as well the robot as a top mount there. A couple of different features. Okay, you have DIN rail, cabinet, and so on in that, and space for all kinds of things. So if you want to basically ever build such a cell or a robot cell that supports ROS2, we have basically now a couple of experiences with building such a thing. If you're interested, just ask us. We can basically provide you plans and also some hints on what can be done and what not. As I said, so we're also going to open source parts of this. So on the one side, we are going to open source the specification of the robot cell. And we're also planning on open sourcing at least a couple of software repositories for different kind of combinations of components that you can have actually in that cell. Why are we doing that? It's not for the good of everything. So on the other side, we actually have a bigger project around that, and you can see that here, and that is this AI Matters project. So in the end, this is part of the AI Matters project where we basically try to create testing environments, and this is basically what you see here is basically the setup that we're currently planning for that. So on the one side, we're going to set up a couple of manufacturing lines, so one collaborative, one high speed with different kind of robot cells. We're going to have a couple of just robot cells for companies to run tests at Fraunhofer IPA, and then we'll also get this mobile robot test range to basically stage logistics and warehouse environments. Plus, that will be great for the NVIDIA guy to know. We're going to buy a couple of compute clusters as well for that. And we're going to as well have the vision test. So if you're interested in having some of the newest hardware for these kind of tests, we're going to get that. And it's going to be ready hopefully in June next year. A couple of other projects that we've running in the European Consortium. So on the one side, basically, we're working on CanOpen, and I'll be talking about that tomorrow in the masterclass. Yay! Hope everything works. Then, that's basically, I would say now it's more like a global effort is this industrial CI, so we have a lot of contributors for that. There's the UR driver that is driven by our members, Universal Robots and FZI, and EtherCAD is basically iCube Institute that is developing EtherCAD driver for ROS2. So that's a couple of the projects that we've running. There are more, so if there's any questions, just come to me and ask me. And that's already everything that I had for today. Thank you very much for your patience, and I'm open to your questions.
Yep. Thank you, Christoph. Now, let's open the floor for any questions.
Thank you. Hi, I'm Kenichi from SIT. In one of your slides, you mentioned about model base. Does it mean that you're able to use MBSC to work with on ROS and convert that into ROS codes?
So basically what we have is a meta model that describes how nodes ROS nodes look like. And we as well have a tool chain for, on the one side, dynamic extraction. So that's relatively simple because basically you just use the tools that you have in the ROS ecosystem to analyze what's the interface of a node. But on the other side, we as well have static analyzers that can basically just look at the code of a node and extract, okay, how does the interface of that node look like? So the goal that we have is that already at design time, you know what your system will look like. And that's, I think, one of the big issues that you currently have in ROS is that usually you will only see what we in ROS call the compute graph when you start it up. And then the compute graph is changing in terms of what kind of situation your system is in. And our goal is to basically have a model of your system, of the compute graph, at design time already that describes your system. Yeah, that's basically one of the big things that we want to do there. Though I have to say, so this works for, currently this works for relatively simple systems. In ROS2, sadly, there are a lot of difficult things to model in terms of configurations. So I don't know. So whoever worked with MoveIt knows that's configuration hell. And then you as well have other things like ROS control, which is also a lot of parameters that you have to pass in to generate your system. And then it's not just a single node that gets spawned, but multiple ones. So there are still a lot of edge cases, but we're trying to tackle that. So this is why it's still a bit of research there, yeah.
Is there any other questions? No questions? All right. If there isn't, then we have come to the end of the sharing by Christoph. Let's once again give a round of applause to Christoph.
Thank you very much.